So last time we introduced the concept of a conditional statement. And a conditional statement is read what? P implies Q, or if P then Q, or Q if P, or P only if Q. Notice that order there. Or when P then Q. Symbolically, it's written like this, P arrow Q. And remember, the only time a conditional statement is false is when P is true, but Q is false. And so we've got the following logic table right here. If P is true and Q is true, then P implies Q is true. The only time it's false is when P is true and Q is false, so that's false, and everything else is true. A little bit of the language. P, which is the first proposition that appears in a conditional statement, is called the hypothesis, the sufficient condition, or the antecedent. Q is called the conclusion, the necessary condition, or the consequent. All right, there's also this concept of logically equivalent. Two propositions are logically equivalent in case they have the same truth value in every possible case. And if they are logically equivalent, then we use a 3-bar equal sign to indicate that. So that's read P logically equivalent to Q. And last time in class, I mentioned De Morgan's laws, which is a way to pass the negation inside of a conjunction or a disjunction. And we actually ran a truth table to show this claim right here, I believe, that the negation of P and Q is logically equivalent to the negation of P or the negation of Q. And so here is this truth table that we looked at in class. Again, all combinations, true, 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 false, false, true, and false, false. The top line, the inside, P and Q would be true and true, which is true, but the negation of true is false. And if I look at this statement, what? P and Q are both true again, so I get what? False or false, which is false. So they agree there. We can check the next line. What do we have? True and false on the inside, which is false. The negation of false is true. Or if I look at it here, it's going to be what? False or true, which of course is true. Here, false and true in the inside is false. The negation of false is true. If I look at this, it's going to be what? False or true, which is true. Remember, the disjunction or is true if either P or Q is true. And the conjunction, for it to be true, both have to be true. Right? And then finally, we look at this false and false on the inside, which is false. The negation of false is true. And if I look here, it's going to be true or true, which is true. Okay, I think we also ran this statement just to show that it wasn't logically equivalent to this one. And if you notice, in the first line, we're going to get what? False and false, which is false. So that works. But the point is, for them to be logically equivalent, it's got to work all the time. And if I look at the second one, I'm going to have what? False and true over here. False and true is false, but the problem is both of this statement here is true. So the second line is enough to show that these two statements are not logically equivalent. Okay, but if you look at the two columns, it's easy to verify that in fact these two statements are logically equivalent. All right, so last time we were talking about conditional statements. So we have a conditional statement, P implies Q. The converse of P implies Q is switching the roles of P and Q, so that's Q implies P. The inverse is defined as not P implies not Q, so you take the negation of the first implies the negation of the second. And the contrapositive is not Q implies not P. So all these things are starting from that conditional statement. And I said today we're going to look and see some of the consequences of that. And in particular, I'm going to claim that the conditional statement, P implies Q, is what? Logically equivalent to not Q implies not P. Another way of saying it is the conditional statement is logically equivalent to the contrapositive. How do you get the contrapositive? Flip the order of the P and Q and do a negation. So let's prove that. So again, all possible cases here. I'm going to remind us what the conditional statement says. P implies Q. So the first line is true implies true, which is true. The second line is true implies false. That's the only place a conditional statement is false. And the other two are true. All right. Now I'm going to look at the contrapositive over here for a second. Okay, so we're going to compute the contrapositive, which is what? Not Q implies not P. Well, not Q is false, and false implying anything we know is true, right? Because if the hypothesis is false, the conditional automatically true. What's the next statement? Not Q implies not P. Well, not Q is true, and not P is false. So you've got true implies false. That's false. The next one is what? Not Q implies not P. False implies true, which is true because the hypothesis is false. The conditional automatically true. And the last one is if P and Q are both true, it's going to be true implies true, which is true. Now look at this column here. Look at this column here. They're exactly the same. Hence, I conclude that the conditional statement is logically equivalent to its contrapositive. Now, if I look at Q implies P, that is the converse. Let's look at that. So in the first line, it's what? Q implies P. So true implies true, which is true. The next one is false implies true, which is true. Notice this has a value of false. This has a value of true in this case. That's enough to conclude that the conditional statement, P implies Q, is not logically equivalent to Q implies P. All right, so what have we shown? We've shown that the conditional statement is logically equivalent to its contrapositive. Okay, now let's look. Suppose we consider Q implies P as my conditional statement. That's where I start. What is its contrapositive? Well, the contrapositive is gotten by flipping the roles of P and Q and negating. So the contrapositive of Q implies P is not P implies not Q. Get it? Well, but I've just shown down here that anytime I take a contrapositive, I get something logically equivalent. So from that, I know that Q implies P is logically equivalent to its contrapositive, not P implies not Q, therefore, these two are logically equivalent. By the way, the contrapositive of the converse is the inverse. A lot of stuff to unwrap, but not too complicated. So what have I just argued? And you can also run a truth table to verify. I've argued that the contrapositive of Q implies P is not P implies not Q, and therefore anytime I take a contrapositive, I get a statement that's logically equivalent. Therefore, the converse is logically equivalent to the inverse of a conditional statement P implies Q. And that's all I'm going to say today.